Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of loan data, German loan data, and we have 11 columns at the end of which is a risk category, a risk column, where we have either good or bad risk loans. So I'm going to try to build a model that's going to identify high risk or bad loans in the dataset. And you can see we have features like purpose, duration, credit amount, checking account, savings account, housing, job, sex, and age. So let's hop into the notebook. I'm going to use NumPy and pandas for working with the data. Then we're going to visualize a confusion matrix later using matplotlib.pyplot and seaborn. And for preprocessing, we'll use the standard scalar and train test split function from sklearn. Then our model will be logistic regression today, and I'm importing these three from the sklearn.metrics. They're all there for evaluating the model, essentially. So let's go ahead and import those. And I'm going to load in the data using pandas.readcsv. I can grab the file path to the CSV file over here, copy the file path, paste it in, and we'll take a look. So let's get a little more info about the data with data.info. I noticed there are some missing values here, and it's only in 2 columns that we have missing values. We also have 6 object columns, so we're going to need to perform some encoding to turn them into numeric features. Last thing I noticed about this is that we have a duplicate ID column that we're going to want to drop. So why don't we start preprocessing? So I'm going to create a function called preprocess inputs, and it's going to take in a data frame. It's going to make a copy of that data frame. Then we'll perform whatever preprocessing steps we want on that copy, and then we'll return the preprocessed version of it. So currently this function will just return a copy of itself, a copy of the data frame you pass in. So let's call that x. X will be the preprocessed version of data, which we're passing into the function. So currently, if we have data on top and x on the bottom, they're currently identical, but now we can modify x and compare it to the original data up here. So let's start off with the easiest thing, which is just drop this column that we don't need. So I'm going to go in and say drop duplicate ID column, and we can do that with df equals df.drop. The name of the column is unnamed 0. And we're dropping from axis 1, which is the column axis. So now if I run this and get x, you can see it's gone. And the next thing to do is probably deal with these missing values. So these are some sort of interesting missing values. If we look at, let's look at x.isNA, which will have a true value in a given location based on if there's a missing value there. So if we sum those trues over the rows, we'll get the number of missing values in each column. You can see we have only a few, and the rest of the data set has no missing values. So if I look a little closer at these columns, let's say I look at the savings accounts column, and I want to get all the unique values in the column. I can do that with .unique. You can see there's little, moderate, rich, and quite rich. And then there's these missing values. So it's possible that the missing values were simply not entered, either because there was no data for it, but it's also possible that these are meant to be interpreted as no savings account or not applicable. And this really is there are multiple ways to deal with this problem, but I think because of the rest of the data, because it's a very clean data set, and these missing values only show up in these 2 columns in this very particular case. If you look at the other one, it's very similar. This is checking account. They're very similar columns, and the missing value seems to me to indicate the absence of a checking account or the absence of a savings account. So this is basically more on intuition and just a sense that I'm getting. I'm going to encode the missing value as none. So we'll just change the missing values to be a new value, which represents no savings account or no checking account. Now, however, if I were to see a lot of different missing values in all different columns, I may assume that this actually just means that there is no data entry entered for that value for that example. In which case, I probably would not set it to its own value, and instead I would fill it with the mode of the column. But because I'm getting the sense that it's its own value, we're going to encode. Do that here. Encode missing values as none. So we can do this. I want to do it for both these columns. So for column in, we have savings accounts, and we have checking account. These are the two columns. For each one, I want to take that column, and I want to call the fillNA function on it, which is going to fill any missing values with a given value, and the value we're going to give it here is none. So now if I run this, you see we have none in there whenever a missing value popped up. And if we look at the sum of missing values over the rows again, you see we have no more missing values in the dataset. So that seems like a reasonable way to handle these particular missing values. After that, I think we're ready to start encoding. So we have, I think it says 6 object columns, yeah. So each one of these is going to require a specific type of encoding. And it's if we want to sort of understand what kind of encoding is best for the column, it's a very good idea to get an understanding of what kind of values lie in the column. So we can create a dictionary that will map a column name to x subcolumn dot unique. So this will say we'll take a column name like age, and it will tell us the unique values in that column. And that's for every column in. Now I could do x.columns, but the problem is I have these numeric values, and we're going to get a whole bunch of different values. For example, if you see this, we're sort of cluttering it up because we don't need to know all this numeric stuff, the credit amount, you know. So instead of just doing all columns, I'm going to do x.select dtypes object dot columns. So this will only get the column names for the object columns or the string columns. And now we can see it more easily. It is still a little messy because the unique, I believe these are NumPy arrays, so we can actually display them as a list just to clean it up a little bit. Alright, so now we can see each column name and the kinds of values that lie in it. And what's also useful, if I just put this down here, instead of showing a list, we can get the length, so the number of values in each one. And so with these two bits of information, we should be able to figure out what kind of encoding is best for which. So there's essentially 3 kinds of encoding. Not entirely, but the 3 we'll be using is binary encoding, which essentially is just going to take a column that has 2 values, and it's going to map one of those values to 1 and the other one to 0. And this is like the most basic form of encoding, but it requires the column to have 2 values. And this, it doesn't really matter if there's an order between the values, because the whole column will just be turned into a single feature that represents the presence of the positive value of our choosing. And it looks like we only have 2 candidates for binary encoding, which would be the sex column and the risk column. This is actually our target column, but we also want to encode it. So, how to binary encode? It's going to take in a data frame, and it's going to start by creating a copy of it. And then we want to pass in, along with the data frame, the column we want to encode. But we can write this function in a way so that we can pass in all the columns at once. So I'm going to pass in all the columns, but I also want to specify the positive values that are coming in along with it. So which value is going to be converted to 1. So I'm going to pass in a list of tuples that match columns to positive values, and we'll call that list columns with positive values. So this is a list of tuples, so we can iterate through for column, comma, positive value in this list of tuples. Whoops. uh, for each pair of column and positive value, we're going to take the column and we're going to apply a lambda function to it. So for every x in the column, for example, x would be male or female depending on the example, we're going to send x to 1 if x is the positive value, and otherwise we'll send x to 0. So this is all you need to do. We're saying for each column and positive value pair, we're going to change all the values in the column that are the positive value to 1, and all the others to 0. And that's it. We can return df after all that is done. So if we now binary encode the sex and risk columns, we can do this with df equals binary encode, which is our function, and we have to pass in a data frame, which here is just df, and we pass in this columns with positive values variable, which is a list of tuples, like I said, and each tuple is going to have a column name and a positive value. So we're doing sex and risk. So in the sex column we have male and female. We can choose male to be 1. That's just the standard convention, but we could also choose female. So sex is the column name and male is the positive value. And then the other column we want to do that for is the risk column. So risk is the column name. And the positive value, it may make sense to make the positive value good, but if you think about the task we are performing today, it's more like useful to try to predict which of the loans are high risk, or which of the loans are bad. And if we look at the distribution of the types of loans we have, so x sub risk dot value counts, which tells us how many of each value we have in a column. You can see we have more goods than bads, so this model is really going to be geared towards trying to predict bads in the data. And so we want to, I'm going to encode bad as the positive column. So we're going to send good to 0 and bad to 1, because we're thinking of bad as sort of like the goal. So we're trying to find positive instances in the data. But of course, you could absolutely make good the positive value if you wanted to. But I'm here going to make it bad. Alright, so now if I run this and pre-process the data and take a look, you can see both sex and risk have now been converted to 0s and 1s, depending on whatever we specified as the positive value. Alright, so we're done with 2 of these. Now we have housing, savings account, checking account, and purpose. So there's 2 other kinds of encoding that I'm going to use. One is called ordinal encoding, which I think it will do next. Ordinal encoding deals with columns that have more than 2 values, but the values in the columns take on a specific order. So you can see here the savings account and checking account columns have an order between the values. You can order these in ascending or descending order. So we're going to do that. We're going to create a function called ordinal encode. It's going to take in a data frame, and this time instead of passing in a list of tuples with the columns and positive values, I'm going to pass in a list of tuples with the columns and orderings. So we're going to specify the order that we want for the column and pass it in along with the column name in a list of tuples. So we'll start by creating a copy of the data frame again. And now for every column and ordering in this list of tuples, we're going to take the column, and again here we're going to apply a lambda function to it. Apply lambda x. And here we want to send x to basically the index of x in the ordering that we pass in. So let's say let's say we're doing this one. Okay, checking account. So here's our list of values. Let's order it. So none comes first, then little, then moderate, then rich. Okay, so here's an ordering. If we index a given value, let's say rich, in the list, we get back essentially it's an integer that represents its location in the list. If we did none, we'd get 0. If we did moderate, we'd get 2, and you get the idea. So we can use this sort of format to sort of convert each value into its integer equivalent in the ordering. So over here, I'm going to map x to ordering.index of x. And that's what that's doing. And we're getting the ordering from the pair that we passed into the list of tuples. All right, we're going to return df, and now let us ordinal encode the, what are the two? We have savings account, saving accounts column, and checking account columns. Savings accounts, and checking account columns. Okay. So for this, similar to how we did with binary encode, df equals ordinal encode, passing in the data frame, and then we pass in columns with orderings. This will be a list of tuples as well, so we need to specify the column name first, which will be savings accounts, and that's going to get mapped to an ordering of values, and you can see here it is. So it's a lot like the one we have for checking account, except we also have this quite rich value. So let's put that at the end. Put rich after that, and I believe that should do it. These are on top here we have the ordering for the savings accounts in the order that we desire, and on the bottom here we have the ordering for the checking accounts in the order that we desire. So let's grab that for the savings accounts, pass that in, and then we want to pass in checking account as the column name, and the ordering here is going to be, where is it? This one. Okay, and now if we run this, columns is not defined. Oh, I accidentally did columns, so let's go ahead and just change that to column. Okay, if we run this and take a look, we can now see that these have taken on values between 0, 1, and well, there's actually, in the savings account, it will take a value between 0 to 3, 0, 1, 2, 4, 0, 1, 2, 3, 4, and in checking account, it will take a value from 0 to 3. And you can see those are present. And now if we run this, we only have 2 columns left. And so these are columns that take on more than 2 values, but there's no clear ordering between the values. One might argue that you could order the housing column, that you could say free comes first, then comes rent, then comes own, but it's not really like that. There's more information carried by knowing exactly what the person is doing than by just boiling it down to a single ordinal feature across a range of values. So for these kinds of columns, we're going to use one-hot encoding. So let's create a function, one-hot encode, and this will also take in a data frame. And I'd like to demonstrate how what a function from pandas called getDummies, which takes in a column. Actually, not df, we'll do x sub, and let's use the purpose column. So if we get the dummies for the purpose column, this is what happens. All the unique values that were originally in the purpose column now get their own columns. And for a given example, we have all zeros and then a single one wherever the original value showed up. So here, for example, 0, we have radio, TV. So for the first 5 examples, we have radio, TV, education, furniture and equipment, and car. So over here, you can see the 1 show up in those columns, respectively, for each location. So this is going to be the way we encode the values in the purpose column and in the housing column. So I'd also like to point out that we can include a prefix here, maybe capital P. And whoops, and that's just going to add a little p at the beginning. And this is useful so that we know where these new columns originally came from. So what I want to do here in the one-hot encode function is pass in another list of tuples, but this time it will be a list of columns with prefixes of our choosing. Alright, and we'll start by creating a copy of our data frame again. And then for each column and prefix in this list of tuples that we're passing in, we're going to create the dummy columns to start. So these are the dummy columns that we created with pandas.getDummies. So up here, we're going to create dummies, store it in dummies. That will be pd.getDummies for df subcolumn. And we want to specify the prefix as the prefix that we're passing in with the column name. Then we're going to concatenate together. So with pd.concat, we're going to concatenate the original data frame and the new dummies columns side by side. And we'll store that in df. So now that we have a whole data frame with the original data and the new dummies, we can drop the original column from which we created dummies. So it's no longer of use to us. So then we can return df, and that's all we need to do. So now let us one-hot encode. What are the two columns? Housing and purpose. Housing and purpose columns. So df equals one-hot encode, and we're going to pass in df, and here we want to pass in columns with prefixes, which will be a list of tuples matching a column name to a prefix. So just two columns here. We're doing housing and purpose. So we have housing, and we're going to match that up with, how about h just as a prefix, and then purpose, and we'll give that a p prefix. Alright, so if we run this, take a look. Here we are. We see we have all these one-hot columns, these dummy columns, added to the end of our data frame, and the original housing and purpose columns are no longer there. So with that, I believe all of our data is now in numerical form. So we're done encoding our columns. So now we're going to split and scale. So by split, I mean let's take what we're trying to predict. In this case, it's the risk column. Let's take that out of the data frame and give it its own variable. So let's split df into x and y. Y will be what we're trying to predict. So y is just going to be the risk column. And we'll make a copy as well. And then x will be the rest of the data minus the risk column. So df.drop risk. And we're dropping from axis 1, which is the column axis. Okay, now instead of returning df, I'd like to return x and y, and we'll store that in here. So now x no longer has the risk column, but we can get that from y, which is just the risk column. Alright, and then now that we've split it sort of vertically, taken out this y, let's split it horizontally with a train test split. So we're going to take some percentage of the data set to train our model on, and then we'll evaluate the model on the rest of the data. So we can do this with the train test split function from sklearn, and we'll pass in x and y and specify a train size. We'll use 70% of the data to train the model on. And this function also shuffles the data for us, so I'm going to include a random state as well. This could be any number. It's just going to ensure that the shuffle and the split are always made in the same way. And then that will return 4 values: xtrain, xtest, ytrain, and ytest. And so I want to return these 4 values down here and get them back over here. Okay, and xtrain looks like this. It's just 70% of the original data, and ytrain is also that same 70%, but just the risk column. We also have xtest and ytest, which is the other 30%. Alright, now we'll scale the data. So currently all the columns in x take on a different range of values. We have 0s and 1s in this one. Here we have all the way up to 5,000. So we want to standardize the data frame so that each column takes the same range of values. And we can do that with a few different methods. We're going to use a standard scalar, which will give each column a mean of 0 and a variance of 1. So let's create a scalar object. This will be the standard scalar from sklearn. And we're going to fit the scalar to just the train set, xtrain. And the reason only to the train set is because in practice you might not have access to the test set. So when you're pre-processing, it's always a good idea to, whenever you're fitting an object or something, you always want to fit only to the train, because the model itself you're only fitting to the train. So it's good. You want to sort of pretend that you don't have access to the test set at the time of pre-processing. Alright, and then we're going to transform with scalar.transform both the train set and the test set using the fit that we have just to the train set. So this will return the new xtrain, and this will return the new xtest. And I'd like to point out that these return NumPy arrays. So if I look at this, you can see it's not so nice to look at. So I'm going to turn it back into a data frame after it's done. And we'll keep the column names the same as x.columns. Alright, so let's just do the same thing for this one. Alright, and take a look. Alright, you can see that the data is back in data frame form with all the column names intact, but all the columns have been scaled to have mean of 0 and variance of 1. So if we look at the means, xtrain.mean, you can see the mean of each column is very close to 0, and with the variances, they are very close to 1. Okay, so we're ready to feed this into our model. Ytrain has not been scaled. We don't want to scale our target. We just want this as a categorical variable between 0 and 1. So now let's train. Okay, I'm actually going to sort of change this a little bit. I'm going to change this to helper functions. And then down here, after we define our functions, we will preprocess, which really just consists of calling this one function. Okay, now training. So let's take a look at the value counts of ytrain. So this is the class distribution. How many of the values are high risk and how many of the values are low risk. And so I'm going to create a logistic regression model. This is the logistic regression model from sklearn. Very simple model. We're going to fit it to xtrain, ytrain. Alright, and now to evaluate the performance of the model, I am going to create another function called evaluate model. And that will take in a model, and it will take in a confusion matrix. Sorry. Actually, it's going to take in just the test set, the so xtest, ytest, and a classification threshold. So let me show you what this means. So if we just take model.score to evaluate the model on the test set, xtest, ytest, we just get a single accuracy value. And so by default, this is just making classifications based on which of the two classes had a higher probability. So if I do a model.predict on xtest, here are the actual classifications that it made. But if I do model.predict proba for probability, you can see it actually returns probability estimates for each of the classes. We have the negative class and the positive class. So you'll notice that they both always sum to 1. So let's just focus on one value. We'll focus on the positive probability. So here is its sort of measure of its confidence that a given example is positive. And this will always match up with model.predict, just model.predict. So if I check this, you can see that the first one, this is less than this, so we have 0. Because because there's only two, this is sort of it has to be greater than 0.5 to be classified as 1. So if we look down and find one that's 0.5 or more, you can see that corresponds to the 1. And then most of these, here we have another 0.51, that's this guy. And down here we have a 0.5, that's this guy. But all the ones that are under 0.5 are going to be sent to 0. So if I ask a question, is this greater than or equal to 0.5? I'm getting a true or a false. And I'm, again, just looking at these values. So these values are actually, if we convert this to, I do as type numpy.int, and this value here is going to be the same as our predictions. 0, 0, 0, 0, 0, 0, 1. And over here we have 0, 0, 0, 0, 0, 0, 1. So these are actually following the exact same form. So if I just want to get this value and not the first one, I just want to limit it to this, I can apply a map. So I'll be mapping a lambda function to this thing. So the lambda function I want to map is going to be, let's take x, which is going to be a single one of these little lists of 0, 1 and 0, and let's just change it to x sub 1. So we're saying only focus on the second element of the list. And if I turn that back into a list afterwards, then we have just the second column of that array. So these are the same as the predictions. This is just the positive classification. So the reason I'm doing it like this is because now we can actually go in and change this threshold. And by default, you can see it's using a 0.5 threshold. But in this case, we have some imbalance in our data. Let's say we want the model to be extra sensitive to, we want the model to be much more likely to pick positive, to make positive predictions. That means we can just lower the threshold, and you'll see many more are coming up positive, because it requires much less for the model to make a positive classification. If we lower this all the way down to like 0.1, you can see they're almost all 1s. Whereas if we raise it, let's say 7.5, you can see they're getting close to being all 0s. If I do 0.9, I'm sure they actually are all 0s. So by default we have 0.5, but I want to see how if we change our classification threshold, we can actually get a model that does the task better for us. So in the evaluate model function over here, I'm passing in the classification threshold that by default we can have as 0.5. And this is just going to calculate essentially this. It's going to create this group of predictions based on the classification threshold that we pass in. So I'll copy that in over here. And I'm going to call this ypred. So actually first I'm going to make ypred just be this thing here. So here's ypred, which will be this here. If I just run this, you can see it'll be this thing again. And then what I want to do is say, let's map the guy to ypred. So after this is done, oh, okay, let me just return ypred to show you. If we call evaluate model, let's grab this. This will return a set of predictions, but we can change this to return a different one. So if I make this really low, we'll have, oh, sorry, I actually didn't plug it in. This should be classification threshold, not 0.5. You know what I mean? So there we go. All right, now they're all 1s. If I make this 0, I believe they'll absolutely all be 1s. And if I make this 1, I'll make them absolutely all 0s. So we want something in between. Sorry, not 5.0, it should be 0.5. And hopefully something that maximizes the model's ability to classify high-risk loans in the data. So I don't actually want to return this. I want to return the accuracy score that we get from this set of predictions. So I'm also going to have a set of true values to compare it to. This will just be taken from ytest, but I just want to make that into a NumPy array. And then I'll print out the test accuracy for a given classification threshold. We'll display this to 2 decimal places with a % after, dot format, and I'll pass in, I'm going to use the accuracy score metric. This is the same as calling model.score, but it allows us to get the accuracy for any set of predictions, not just the default set. So accuracy score, passing in y true and y pred, and I want to multiply that by 100 so we can get it in a percentage form. Now if I run this, we'll get a test accuracy, and by changing the threshold, we can actually change the accuracy we get. So at the high end, low ends, this is obviously going to be pretty bad. Although it's not that much worse the higher it goes. But 0.5 by default. Okay, so then I want to show a confusion matrix and classification report. So confusion matrix is a way of seeing where your model is making classifications. So I'm going to store it in CM and call confusion matrix. I'm going to pass in y true and y pred again, and then we can print it out. So this is the confusion matrix, and currently it looks it's not so nice to look at. So why don't we spruce it up a little. We'll create a new matplotlib figure with a figure size of 8 by 8, and I'm actually going to plot a seaborne heat map of CM and plt.show. So this should be a lot nicer than just seeing it as text form. However, it looks all whacked out, and we're going to have to do a few adjustments. Well, first I want to see the annotations. So annote equals true. So that will show the numbers. However, some of them are showing in scientific notation, so we can fix that with fmt equals g. And then also, our lowest possible value here is 18, so which is displaying as black, but I want to set that to 0 because the lowest possible value we could have is 0. Alright, so the colors are a little nicer now. I also don't need this color bar here, so I'm going to turn it off. C bar equals false. And I want to give it a nicer color scheme, so I'm going to give it a color map of blues. Okay, so it's looking pretty good now. So here on the X is our predicted class. The predictions we're making, so why don't I give it an X label of predicted. And on the Y, we have the actual values. So here's our predicted values, and here are our actual values. And let's just give this a title, confusion matrix. Alright, and one more thing I can do is, instead of you seeing it just as 0 and 1, let's put it in English so that we can understand it more easily. So we're going to set the X ticks and Y ticks. First we have to pass in location for the tick marks. We'll use a NumPy A range for that. So generate 2 values from 0 to 2 minus 1. So it's essentially just going to generate the same 0 and 1, but locations. So if we can then pass in the actual labels we want. So not risky and risky. So you can see we have not risky and risky. And you can see that the tick marks are actually at the corner and the middle, which we don't want. So let's shift it over by 0.5 in the locations. Alright, so now they're where we want them. And let's do exactly the same thing for the Y. So we'll grab that and plot.y ticks. Alright, and so this is a pretty good confusion matrix. This allows us to visualize how well our model is doing within each class. And the last thing I want to do is generate a classification report. So I'll call it CLR, and a classification report is just going to give us some more information about the confusion matrix. So I'm going to pass in y true and y pred, And I also want to give it some target names to use, which will just be this list here of not risky and risky. Oh yeah, and I have to print it out. So print CLR. So here it is, and we can also just give it a little header or something. So classification report, new line, hyphens, new line. Alright, and it needs 4 more hyphens. Alright, and here it is. So these metrics are sort of telling us a few things. So precision is a measure of how well we're doing across all categories. So for a given prediction, let's say our risky prediction, we're looking at all of our predictions that we predicted risky, and across both categories, how well did we do. So between these two, within the risky predictions, we actually got 57% of them correct. So that's indicated by this, because 24 out of the total predictions is 57%. So you can see the precision for the not risky category is saying out of all of the predictions that we made for not risky, between or across the categories, 71% of them lie in the correct value. So we got 71% of those correct. Then for recall, recall is a measure of how well we did within categories. So here's risky. This is our risky category. By category, I mean the actual value. So out of all the actual risky examples, how many did we get right? And we got 91. For the risky one, we got 24% right. So here's the correct risky predictions. You can see out of all the risky examples, we got 24% of them correct. And then for the not risky, we have a very high recall, saying out of all of the actual not riskies, we got 91% of them correct. And the F1 score is just a sort of combination of the two. It's a good indication in a single number of how well our model is doing within a given category. So you can see our model is definitely performing better in this class, in the not risky class. And the general reason for that is simply because we have more examples in that class. So there's a few things we can do to work with this imbalanced data. First of all, I just like to take this evaluate model function and put it up in our helper functions. Alright, and then here, I'm just going to remove these and say results. Alright, so the first thing we can do is give some class weights. Well, actually, I guess the first thing we can do is just change the classification threshold, since we already put that into the function. You'll see, when I change this now, let's say I bring it down to 0.1. So this is saying we only need 10% confidence in the positive class in order to make a classification for positive. So by lowering this threshold, I'm going to make a lot more positive predictions. And you can see they've all shifted over here. Now our test accuracy has just tanked because now we're completely failing like a majority of the examples. And if on the other hand, if I make it really high, like 0.9, we're saying we need really high confidence, like 90% or above, in order to make a positive prediction. So that we should see all of them go over here. Yeah, in fact, literally all of them went over. We don't have a single prediction in the risky category. So we have to find some sort of balance between this. So 0.5 was by default, and this is sort of a measure of the accuracy, but the F1 score is sort of a better indication, because we don't just want overall accuracy, we want decent performance within each class. We want to be predicting the riskies when they show up, but we don't want to be too aggressive that we're making a lot of errors and predicting not riskies as risky. On the other hand, we don't want to be too conservative as to like not get the riskies correct and predict everything not risky. So let's find a balance. So we'll try with 0.4. And this, okay, let's actually mark down what we originally had so we can compare. So we started with an F1 score of 0.79 in the not risky category. And then in the risky category, we had one of 0.34. So let's see if we can sort of balance these so that we can improve this score without losing too much of this. So let's lower it to 0.4. Sorry, I've got a markdown block. Okay, so it did go up. It did go up. So by lowering the threshold, we're making it more likely to predict risky. And you can see that overall we are doing better in that category. I believe by lowering it any further, we're going to inhibit the models. Oh, it's saying we're still doing well, but it looks like our precision is going down at expense of recall. So let's bring it back up. Yeah, you can see we have a high precision, well, decent precision of 0.5 and recall of 0.41. Now if I lower this down to 3, our precision is now dropping while our recall is going up. And what that means is we're doing less well in making our risky predictions correct, but we're doing better in getting more of the actual riskies correct. So I don't want to lose too much precision, and I want to see what happens if we bring this up to 0.6. So with 0.6, our recall recall is really going down. So the higher we make this, the worse our recall is. So because the higher we make it, the less likely we are to make any risky predictions. So the balance, the trade-off between these two values is going to be heavily weighted towards the not riskies. So I think 0.4 is looking pretty good for a threshold. It seems to offer a nice balance between the precision and recall, and our F1 score is decent as well compared to the original values. So we only lost about 3 points off our F1 score from the not risky column, whereas we gained about 11 points of the F1 score for the risky. So that seems to be doing well. And then the other thing we can do is using class weights. So class weights will weight the loss function. So class weight, we pass in a dictionary that's going to map each class to a weight. By default, they're at 1, which just means that in the loss function, each class is treated equally. And you'll see that if I raise one of these, let's say I put an enormous weight on the 1 class. This is saying, okay, we're going to penalize bad classifications, bad positive classifications, 20 times harder than we're penalizing bad negative classifications. So if I run this, you can see we're basically completely forgetting about this. Because the model, really all the model is seeing now is the positive loss, because the loss for the negative class is so minuscule compared to this enormously weighted part of the loss function, that we basically just forget about the negative class completely, and the model's only focusing on the positive class. On the other hand, if we bring this to a really high weight on the negative and keep it the same as on the positive, they all go over here, because the model is basically completely forgetting about the positive class. All it can see now is this enormous loss on the negative. So obviously these weights are too big, but maybe we can find some sort of balance that will offer a nice performance increase. So let's try just multiplying the positive by 2. So it's saying let's focus more on the risky. And let's see. Okay, it's not bad. I'm not saying it's great. Our precision has dropped below 50% on the risky, but our recall has gone up substantially. So let's try flipping that. Let's try doing it this way. Alright, so this one really did not help. It's clear that that's not the way to go. Our precision went up slightly, but our recall really went down, and therefore our F1 score as well. So let's try the other way. We're going to try to raise this positive weight until we get the optimal amount. So I don't want to lose too much precision, and ideally I want to keep it over 0.5, because if it's under 0.5, we're essentially not doing the task very well. It's saying we're getting more risky predictions wrong than we are getting correct. So let's try let's try a 1.5 instead of 2. Alright, we still have below 0.5. Our recall has gone up, our F1 score has gone up, and not at too much expense of the precision score. But let's see, maybe why don't we try 1. Well, let's just look at the 1 again, so that we can just jot these down. Let me just copy this in. This is bad. Alright, let's just look at it like that. So, I don't need to see the support here. Alright, so I want to try to find a balance between these values. This is our original value while we're using a 1-to-1, 1 and 1 class weights. So let's see, by changing this to 2, what kind of effect is that having here? So, our recall really did go up a lot, and our precision dropped by 0.4, and I'm not so happy about that. So even though our recall went up, our precision did drop below the 0.5 sort of threshold. So let's try 1.5. Okay, so we only had one 1 point drop from precision here, and we actually did gain quite a bit of recall. So I might be willing to take this because it doesn't look like we're able to get a very high precision using this method. Well, let's see if we drop this to like 1.25. Yeah, we still have 0.49, and we've also lost precision. So it looks like that might be the best we're getting. Let's see 0.75. Yeah, our precision's dropping even more. So it looks like 1.5 weight on the positive class is giving us pretty good performance. We got a slight drop from the precision, but a good amount of increase in the recall. And so our F1 score has gone up as well. And on the positive class, well, it actually looks like, yeah, well, that makes sense. Our precision has gone up in the negative class, sorry. Our recall has gone down, but the balance between them is more fair. And if you look at this, we have a decent number of true positives and true negatives. Only thing I'm not so fond of here is that the trade-off in the precision of the risky category. Alright, but I guess that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.